Okay. Hello, everybody. Let's start today's class. So today, I think first we'll finish the theorem of composition of accelerations. I think I will just talk about one example, and for the final section of this chapter, because it too hard for you guys, I think we'd better skip it. Then, so the after this example, we'll move to the new chapter, chapter 9. So I think last time we have finished and stopped at this page, So we talk about theorem of composition of accelerations. It's more like what we have learned and used theorem of composition of velocities. Do you guys still remember that? So we have like this absolute velocity equal support velocity VE plus relative velocity VR. So we can compare from these vector equations of composition of velocity and this composition of acceleration. So here we have a prerequisite is when the transport motion is translation. Our transport motion should be translation. Otherwise, actually, if our transport motion not translation but a rotation around the fixed axis, then we will have two plus another extra acceleration. We call that 克里奥利科氏加速度。But this part is too difficult for you guys to understand. So I think I will skip it. We do not introduce the final section of this chapter. So we only consider this kind of situation. That is our transport motion in translation. So when the translation motion when the transport motion is translation, the absolute acceleration of moving point, we use this AA. So this subscript A means absolute, equals the geometric sum of its relative, that is AR, and transport accelerations, that is AE. So as for this, actually, according up to the style of the rigid body. So this is maybe the most complex pattern of this equation. But maybe you guys don't keep your eyes on this. We just know some typical or simple example how to use this theorem of composition of acceleration is enough, right? So then we will talk about one example. So let's see, actually, we have talked about this kind of example to learn how to use the theorem of composition of velocities. So this time we'll still use the same example. It tells us the radius of the cam. This is a translational cam. It radius because it has a circular shape with radius r, and it has V0 along positive direction of x, and A0, that is uniform acceleration. So these three quantities are known, right? So let us find the velocity of rod AB when phi equals 60. We also can find its A of rod AB, right? We also can find its acceleration, right? So we can reconsider this example again. So the first is our solution is choose the MP. So, I have mentioned it before. For this cam and follower mechanism, you guys should know that we always select a point on the follower. So here in this example, you will find we choose point A on rod AB as the moving point, and we attach the moving coordinate system onto the cam. So this is typical selection. because when we are thinking about that, we are sitting on the cam. We look at the moving point A, it's very easy to find its relative velocity, right? It's relative motion. So this will be its relative velocity. And here, actually, because the movement of this translational cam, this follower AB will upward and downward movement. Because of this fixed slot, it gallons, it only can along this vertical line. So translational movement upward or downward. So this time we will find actually from this position, if this cam to further move from left to right, then this AB will move upward, right? So this is absolute velocity. And when we use this VA equal VE plus VR, I always an emphasis to MCS. So here in this example, we know that this translational cam have this V0 and this A0 and its motion in the translational movement. So any other different point on this cam will always have same velocity and same acceleration. So do you guys still remember this main characteristic of a rigid body which has a translational motion, right? So here our VE actually is this. So VE is magnitude V equals V0, right? So we can use this to find because our task is to find the velocity of rod AB, actually find VA and AA, right? So let's move to the next page. Actually, we have finished all the analysis. So that is absolute motion is along vertical line AB. So this time it will have upward direction. So we come back to the page, so I do not need to draw this picture again. So and you guys can see this angle, you know. So this line is perpendicular to this line, right? And this VR will perpendicular to this line. So actually this angle should be phi. So that means our three velocity will constitute a triangle. So if I draw here, where is my pen? Sorry. So if I draw here, no? So that is actually this should be our parallelogram, right? Our parallelogram. So since this will, because this vertical line, this horizontal line, so here should be 90 degree. Here also should be 90 degree. So you guys will very easily find actually this is a rectangle triangle, 直角三角形, right? So we are cosine phi equal VA, right? But here our VE is known. So we better use tangent phi, tangent phi. So here from this triangle, tangent phi will equal VE over VA, right? So because we know VE actually is V0, so we have actually what we want to find the velocity of AB, that is VA actually should be V0 over tangent phi. And we also can find VR times sine phi. So you can find from the same rectangle triangle, VR times sine phi, right? Times sine phi equal VE, that is V0, right? VE. So our VR will equal V0 over sine phi. So that is how we use the composition theorem of composition of velocity to tackle this kind of cam follower mechanism to find velocity of rod AB. So after we finish this, we will try to use the same pattern to find the acceleration of rod AB. So let us do this together, right? So back to here. So this time we are going to draw a vector diagram of acceleration shown in this figure. So once again, we should remember that our moving point is A, right? Our MCS attached on cam, right? So our stationary coordinate system will always be Earth around. So we should use the similar pattern of composition of theorem of composition of velocity. So you guys should remember first, we should use this absolute acceleration. We should letter A equal AE plus AR, right? So the process of analysis of this almost the same pattern from what we have finished before up when we do like VA equal VE plus VR. So I'd like to do this together with you guys. So since we know the absolute motion of follower AB will translational movement along vertical line AB up and downward, right? So this time, because this cam will continue move from left to right, we can find actually this cam will push this follower AB move upward. So we guess that is acceleration AA may be also along the same direction of VA. So we give AA like this, right? I hope you guys can understand that. And this is AR. So maybe here a little bit difficult for you guys to understand because when we are sitting on this MCS, on this cam, we look at the point, actually it's more like this phenomenon. We found a point A actually along a fixed, along a fixed circular trajectory or path to move. So you guys should think about natural coordinates immediately. So if this kind of motion, this moving point have a motion along a fixed trajectory, so we'd better use a natural coordinate 自然坐标系 to denote its two opponents of its acceleration. So maybe I should change another color for our on my pen. So do you guys still remember? Let's see. At this position, its curve center is here. Let's see. So it will be AA equal a tau along tau direction and an along n direction. Do you guys still remember? And our a tau will equal what? S2 dot along tau direction. And our an will always equal v squared over rho. Right? V squared over rho. So here, in our example, here should be VR. So actually, in this example, we also know this AR will have two components. Is this transport acceleration. So you guys please pay attention to my description. Once again, when we talk about transport velocity, when we talk about transport acceleration, we always think about there is a point A prime on the cam, on the MCS, right? It's actually the same position of moving point A, but it is a point on the cam. This moving point A, although it contact with this cam, but it's not a point on this cam. Oh, otherwise, it will have no relative movement compared to this cam, right? So this is very, very important. You guys should notice that clearly. So actually, when we talk about this, I will erase this here. No? So actually we will find because this cam has a translational motion, any other 2-point will always have the same velocity v0 and the same acceleration a0. So we will give like this, this is AE, this is AE. So actually, I can rewrite it at here. So our AA equal AE plus AR tau plus ARN. So we'll think about its magnitude, right? Its magnitude and its direction. So AA, we don't know its magnitude. Actually, that's what we want to find. Our task is to find the velocity and acceleration of follower AB, right? But its direction we know actually is parallel to AB or totally along the vertical line AB. And for AE, we know its magnitude will be what? A0, and its direction will be horizontal line point to the same direction of positive x direction, and AR tau, we don't know its magnitude, but we know its direction because it will perpendicular to AC. to eliminate effect. The side effect of this AR tau is we don't know its magnitude. So you guys please pay attention to my description. So I will define a direction, define a direction here. Let me give it this direction a name call conceive one. And then we give the corresponding angle, from the same reason, this angle also should be phi, because this slide perpendicular to this slide and this direction perpendicular to this slide. So here must be phi, right? And so because this angle plus this angle will be 19 degree because just this the same line CA here, right? I just prolong this CA into this and give a positive direction definition, right? So here also should be phi. Why? Because this is vertical line, this is horizontal line. So this angle plus this angle will be 90 degree. And the same angle plus this angle also equal 90 degree. So this angle and this angle will always be phi, right? So after we do this, then we use this very important projection. We project, we project equation 1 onto axis conceive 1, So you guys will find actually when I give this direction, the main characteristic of this direction is AR tau perpendicular to this conceive 1, So when we do this projection, onto this axis conceive 1, you will find actually since this AR tau we don't know its magnitude, but it's fine because when we do this projection, you will find its projection onto this conceive 1 will be 0. So that's how we eliminate its side effect. So you guys should know that when we do this projection, you should from the left side, then to the right side. We should do a projection of one projection from one quantity at a time. So let's say, please you guys follow my steps and listen to me carefully because this thing is not easy for you guys. I hope if you can understand, will be very, very, very good, So we will find AA here. So we try to projection AA onto this conceive 1. So we should, let's say this angle maybe is alpha. So AA times cosine alpha will be its component projection onto conceive 1 and along the positive direction. But alpha plus phi equal 19 degrees. So cosine alpha will equal sine phi. So the left side will be AA times sine phi. We should draw equal sign and think about AE. So you find AE here. So its projection onto this conceive one also will be AE. AE actually is A0, because we know its magnitude. So AE times what? Cosine phi. So we should totally consider its direction because AE cosine phi will along the positive direction of conceive 1. So this is positive. Then AR, because it's perpendicular to this conceive 1, so its projection onto here will be 0. That means we do not need to consider this anymore. So ARN, you'll find actually ARN is on the conceive 1 axis, but its direction is opposite to this positive direction. So we should give what? So we should give minus sign, right? So should, I'm sorry. So here should O, right? So let's see. So here should be what? Should be, we talk about ARN, right? So should be minus ARN. Then we can finish. So back to the page, let's see what the magnitude of phi. So it tells us phi is 60 degrees. So we can use this to find the final result, right? So you can find actually A times sine 60 will be uh, square root 3 over second equal AE should equal a 0. Cosine 60 will be half, right? And what our ARN, let's see, because we know our VR, do you guys still remember that? Our VR times sine phi times sine phi means sine 60 will be square root 3 over 2 should equal with 0, right? Should equal with 0. So actually our VR will be our, if we do the squared, so we have VR squared times this equal with 0 squared. So our VR squared will be 4 times V0 squared over third. And our ARN will equal what? So 4 with 0 squared over 3 over R, right? So we have this should be, I think should be this. Then we should divide this to here. So let's see if we can find so we will time uh, uh, second over square root third both side of this equation. So we have AA will equal what? Equal, let's see, times A0 plus this should be what? So can you guys understand this process of calculation? So I think it's not very difficult. So you guys can find actually our final result is the same to this because this second and this second can be eliminated. Then this 1 over square root 3 actually is square root 3 over 3. So you guys can find actually this is the same to this. So I have after introduce this example and tell you guys how to use this vector equation about the composition of theorem of composition of acceleration to find some things. So I hope you guys can understand, but if you can't, that's fine. I think I hope at least you guys have some impression, right? So maybe you guys can come back to our textbook to just look at this example again and try to understand the whole process. So I think that's all for this example. We have finished all this. Uh, Actually, we should talk about the final section of this chapter 8, theorem of composition of accelerations when the transport motion is rotation. But this part is a little bit difficult, so I decided we do not learn this section anymore, but I can give you a quick conclusion to you guys. So you guys to have an impression is enough. So let's see this. Actually, this is final result. It means so I only need you guys have a basic impression of this. So please consider this description. So when the transport motion is rotation, the absolute acceleration AA of a moving point equals the geometric sum of its transport acceleration AE, its relative acceleration AR, and Coriolis. Actually, we Chinese always call that 科里奥利. Just use the use this. This is a famous scientist of maybe from Australia. Maybe right, maybe not correct. 科里奥利, it's just some guy's name, because this guy first find or discovered this 科氏加速度. That means we have absolute acceleration AA, we have transport acceleration AE, we have relative acceleration AR, then we also have to give another extra acceleration that is AK. Just use the first letter of his name. So actually in our Chinese textbook, we always write this AK with AC, so just use the first letter of its name. So actually this AC will just equal 2 times omega transport VR. So although this is a cross product, but the main problem, our task, or almost all the normal engineering problem is plane problem. So we always use this expression to find its magnitude. So I think maybe this part is too difficult for you guys to understand. So that's fine. You just have a little impression is enough. We will do no. I will do not do the further explaining, including some example. So this is the final page of chapter 7. I think to chapter 8, right? I'd like to give you guys a homework. So please, you guys try to finish by yourself. And the next time, if you guys feel it's very difficult to finish, maybe we will do it together at next time, right? So this is a homework of today. So I will cut it into our WeChat group. So you guys, maybe I can give you some hint. So we have O1A equal O second B equal 10 centimeters, and O1 and O2 equal AB. So you guys will be find actually this is parallel, 平行四边形, right? Do you guys still remember we have the conclusion when this false line is a parallelogram, 平行四边形, then this AB will have a translational movement. So AB will be a rigid body and has translational movement. So that is a very important conclusion. It tells us there is a color, maybe a sleeve, who have inside a hole, and AB rod can through that hole. So actually, this color C or sleeve C have relative movement compared to this AB. And C is the pin connected with the bar CD. So it's more like a follower of a cam mechanism. So that means this CD only can move along this vertical line. So it also is the rigid body which has the translational movement. So it tells us to try to what? tell us try to determine the velocity and acceleration of bar CD when phi, here is phi equal 60 degrees. So you guys just need to use this VA equal VE plus VR, and this AA equal AE plus AR. Because here, our moving point should be C, and our MCS should be what? Should be AB. So you can use what we have learned, use these two vector equations to find velocity and acceleration of CD. So because this fixed slot guidance, so this point C is absolute velocity and absolute acceleration will always along vertical line CD direction. So you can you can know the absolute velocity and absolute acceleration is direction, and its relative movement will always along AB direction. Then the transport velocity and the transport acceleration, you should think about O1A. Because point A it is a point on AB. It is also a point on this rigid body O1A, which have uniform angular velocity around the point O1. So you can easily find actually VA here, right? And it's AA here along this direction, AA. And VA equals omega, let's say, O18R, and this AA will be omega squared times R, because it's a constant angular velocity. So omega dot equal angular acceleration equals 0. So this AA only have one component, that is norm AN, because it's A tau. Because it's A tau should equal R alpha, and alpha equals 0, so this one is 0. And its normal component will be omega R squared over R. So R will equal omega squared R. So that's our hint of this example. So the the other things should you guys do it by yourself. So all of you guys please try, try to finish by yourself. And next time maybe we should do this together, right? I think that's all for this chapter 8. And it is time for us to move into the new chapter. So I think today the last class of week 10. Do you guys remember actually our total time of this class is 16 weeks. So next time will be the 11th week. So we also have a lot of things to learn. So it's very I hope you guys can do some review or can read the textbook again when I finish some chapters introduction. So actually, you guys find this chapter 9 called plane motion of a rigid body. It means plane motion, we Chinese call that 平面运动. And this will be the final chapter of the second part of this course, because the second part we are talking about the kinetics of body system. So we call that plane motion will be 平面运动. So do you guys still remember? Actually, we have finished the introduction of two patterns of simple motion of a rigid body. So one is the translational, right? One is translational. Translation. So when a rigid body have a translational movement, I always said that any other 2 points on the same rigid body will always have same velocity and the same acceleration. Another simple motion of a raised body will be rotation, right? Rotation around fixed point. Then if we have a body like this, let's see it OA, and it have a uniform angular velocity. So any point on this raised body, we can very easily find its velocity and acceleration, right? So let's see, this raised body is a little bit complex. It also have angular acceleration. Then we can know a point on this raised body, its V will equal omega r, its A will equal a tau on tau direction and a n on n direction. And our a tau will be r alpha, and our a n will be omega squared r. And here this r means that point, it distant from that point. Let's see, that point is, let me see, it's C. Actually, that point C is distant from the rotation center O, right? So any other point on this same rigid body, you only need to know its r, you know? But a different point on the rigid body will have different r. Then other things are the same, because all the points on the same rigid body will share the same angular velocity omega and the same angular acceleration alpha, right? That's what we have learned before, the first chapters of this second part. And the final chapter of this, we will talk about the complex motion of a rigid body. You know, a complex motion of a rigid body. So that is plane motion. That means its motion is very complex. It has two components. One is translation, another is rotation. So we can think about that. Actually, this body, its movement is a little bit complex. At the same time, it have translational part, also have rotational part, right? Actually, these two parts is independent. Although it happens at the same time, we can think about that. It happens from one time to another time. This assumption, we call that 运动叠加原理, theorem of moment superposition. So that's the brief introduction of this whole chapter 9. And actually, there are 4 sections we will introduce one by one. So the first one will be introduction. We'll see that later. The second is plane motion can be decomposed into translation and rotation. So I just finished this introduction because these two components of this complex plane motion is independent. So we can decompose it into translational part and rotation part. And we are going to talk about the equations of plane motion, right? And the third section will talk about the velocity of a point in a plane figure. The final one is a hard one, a little bit difficult to understand, especially for you guys. We are going to talk about the acceleration of a point in a plane figure, instantaneous center of zero acceleration. And the good news is when we talk about the acceleration, here we do not need to consider AC, 科里奥利 or 柯氏加速度, because our transport motion here in this whole chapter will always be translation. So that's all for the whole chapter. Today we don't have enough time to finish our sections. We will learn that one by one, right? I will just slow my speed, and I hope you guys try to listen to me and try to understand. And I will highly recommend it that you guys should look our textbook again because it's true, it's a little bit difficult for you guys, right? So let's move the first section, do a brief introduction. So let me read the first paragraph. You guys can think about, is this true? In engineering, we often encounter the plane motion. So once again, this plane motion of a rigid body, which is more complicated or complex, right? So investigation into this kind of motion is conducted on the basis of translation and rotation of a rigid body, which we have learned before, right? Using composition and decomposition of motions, 运动的合成与分解。Decomposing a plane motion into translation and rotation, right? And employing the theory of composition of motions. Here means in Chinese 运动合成. So composition means synthesis. Synthesis. So we trying to call that 合成. Motion means movement, 运动. The formula for finding the velocity and acceleration of a point in the rigid body can be derived. So if we try to do this, the first thing we should give the definition of a plane motion of a rigid body. So you get, please follow me. The distance between any point in the rigid body and the fixed plane always keeps unchanged during its motion. In other words, any point in the rigid body moves in a plane parallel to the fixed plane. The motion described above is called the plane motion of a rigid body. So let me repeat that. The distance between any point in a rigid body and a fixed plane always keeps unchanged during its motion. In other words, any point in the rigid body moves in a plane parallel to the fixed plane. The motion described above is called plane motion of a rigid body. So I think maybe I should give you guys a picture to help you guys to understand this definition. So I think you guys should know train, right? We should know train. Actually, train is a very typical vehicle. Actually, we have two rails, and at each rail, it will have a lot of wheels. So I just try to draw this. This is a pair of wheels. This also is a pair of wheels. And these two wheels should on its rail, right? So if I have a fixed plane here, this plane is fixed, You just consider these two wheels on one rail, So that means any point on this movement of this mechanism, we can find all these points have a fixed or the same distance to the fixed plane. It is a fixed plane, right? So we call that this kind of movement is plane motion. So actually, here is another example. We will see that later because it is time for us to have a short break. We will restart at 11:10. So please, you guys have a rest. I'll see you then. I guess, are you still there? Listen to me. I think this is the first time when I said, you guys please have a short break. There, there are no any other gentleman reply to me. So actually, today we have, I received a news. Actually, we have the new name list of our mechanical grade 2021, you know? So if I open this file, you guys will find, you guys will be find actually all your guest name and your number here. So you can see actually about the latest update, our number of students on this class, mechanical engineering 2021 should be 16. But I think our WeChat group, uh, you guys will find if I drag it into here, only have 16. But here 16 including me, right? Including me, the first guy. So I think there should be a gentleman do not uh, in our group. So can you guys drag that gentleman into our WeChat group? And please, all you guys should pay attention to your attendance because we have to have the finish examination, right? So if there is some guy never showed up on our class and never sent me any your homework to me, and the worst thing is it never showed up and never finished the final examination paper. So how can I give you marks? So I don't know or which one will be that guy, but you will fail this examination, right? So if you guys can find which one do not in our WeChat group, please add him here, right? Please add him here. I don't know how to, I cannot find which one do not in our WeChat group. So I think you guys should pay attention to your attendance. So maybe one or two times or several times you don't show up, but you at least should show up many times. I should know your name. I can see you on the list, you know? So you guys can find, so almost at each class time, I will have this picture to show you guest attendance. You see? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Almost all the time we only have 10 to 11 students attendance our class. So maybe each time there will be 5 to 6 students do not attend our class. So how can you guys finish your final examination? How can you guys get your credit? How can you graduation finally, right? So maybe that should tell you guys in advance because our course is a little bit difficult, right? So that's all I'd like to tell you guys, and I will finish. I will continue our new content. So actually, the first we should know the definition. What is plane motion? So you guys can look at this very beautiful picture. Actually, this called crank rod mechanism. I can show you guys its Chinese name. We call that because crank. We always call that 曲柄. 曲 means not straight; it's curved. 曲柄. That means this rigid body, it can rotate around point O with 300 degrees, right? That means this OA will have a rotation around point O. And rod means 连杆, you know? Liangar means this rigid body AB. So you can find actually this AB, it do not connect with frame. Do you guys still remember what is frame? Frame actually is our SCS, stationary coordinate system. It's Earth's ground, it never move, it's fixed, right? So actually this AB connects with crank OA at here with this pin and connect with another slider, this yellow slider at point B. So it do not connect with frame directly. So we call that Liangar. Actually, it will have plane motion because it not connect with fixed frame directly. So it will have complicated movement. So that means plane motion is this rod. So actually the whole name of crank rod mechanism, we Chinese call that mechanism or mechanism with 机构, right? So actually mechanism is body system, right? It's the body system because we have a lot of rigid body, we have a lot of constraints to connection one body to another, then it will constitute a very useful mechanism. So you guys can find actually this is the principle of combustion. Do you know combustion? 内燃机. That's how our car can move with the combustion of gas, 汽油, you know. And I think that is 曲柄连杆结构. Right? Actually, when this crank OA rotates around point O with one solution to another, that means it rotates and rotates and rotates. Then the force will from A along direction AB into this ladder, and this ladder will, according to the guided slot, will have a vertical movement up and down, just like what we have mentioned, cam follower mechanism, right? So because the rotation of this OA, our final tool of this yellow slider will always have a movement, translational movement up and down, up and down, you know? So actually this rod AB will have a plane motion. So here it tells us since A moves in the circular path, no, this is circular path, and this R will be the length of OA. And point B move along a straight line, this vertical straight line. The motion of rod AB is neither translation nor rotation about a fixed axis, but plane motion. Plane motion means 平面运动. No? 平面运动. That's the main task of this whole chapter 9 we're going to talk about. So first, that's the definition of 平面运动. And here in the other example, the same thing. So if we have animation will be great for you guys. So maybe you can take your time to find some video by yourself from internet, right? So let's see the second thing, how to simplification of plane motion. So you guys, let's say this green is what? Is the rigid body, which have a plane motion. You know, it has a plane motion. So its typical characteristic is we have a fixed plane here, fixed. So that means any point on this body, although this body have a complicated plane motion, but any point on it will always have a fixed distance to this reference plane. You know, so that's why we call this movement is plane motion. right? So if you guys can totally understand that, this time we will do some simplification. So a plane motion of a raised body can simplified to a motion of a plane figure. Plane figure we call that 平面图形. So I will show you guys the reason later. 平面图形. Why we can use the plane figures motion to denote a plane motion of a raised body. You see? So you can see, as indicated in the figure, when studying a plane motion of a raised body, we do not need to consider its geometrical shape and size. Why? We just need to considering the motion of a plane figure is enough. Why? Why? So you guys can think about that. Imagine that, not for real, just imagine we have a yellow plane second, which is perpendicular to this fixed reference plane. So this plane can cut our green rigid body into two parts, right? Actually, we will have a section shape, 截面图形. So if I arbitrarily select a point on this section figure, let's say it's point A, and I draw a vertical line A1 to A2. So you guys can think about that. Although this green rigid body have a plane motion, but this line A1 to A2, its motion will be translational. Can you guys understand that? Translational. Because this line will totally move with this green rigid body, but it will never change its orientation, right? It always keep its vertical direction. No? So this line A1, A2, it is a line on this rigid body, but its motion will only translation. Translation. Because although this rigid body have a plane motion, maybe it will move from one position to another position. Maybe it also have some rotation, but this A1, A2 will always keep its orientation, right? So that means this line is translational motion, translational. So if you guys can totally accept that, that means because raised body including a line, if its motion is translational, that means any other 2 points on this line will always have, that means VA1 will always equal VA2. AA1, right, will always equal AA2. So that means we only need to study one point on this line is enough. If we know its velocity and acceleration, then any other point on this vertical line is velocity and acceleration we will know, right? So since we can draw a lot of this kind of line, here, until all this line it intersects and point with this section fulfill all this, the whole section. So that means we only need to study this plane figure, right? So we only need to study the plane figure is enough because it can totally describe the plane motion of a raised body. That's why we do not need to consider its geometrical shape and the size of this raised body. So can you guys understand this? That is so-called simplification of a plane motion. We only need to consider a second figure is enough, right? This is the second thing. One is the definition of plane motion, right? So let's continue. We will move to section second. To talk about the plane motion can be decomposed into translation and rotation. We'll talk about the equation of plane motion. So let's talk about that. If let's see this how to describe this color. So I think it's shallow blue. Is that green? Or there's some word of English to describe this color. You guys can help me out. How to describe this color? Maybe I think it should be shallow blue, right? Or maybe 青色. Am I right? Maybe I'm not correct. So let's see. This is the plane figure. It denotes plane motion of some rigid body, right? So we are going to talk about its equation. So we have a fixed coordinate system here, x or y. That means we have this short line means with the time change, this position O and this orientation of X and Y will never change, right? So this is a fixed coordinate system. Also, it's more like SCS from the last chapter, right? So if we determine the position of a plane figure, which represents a plane motion of a rigid body, so only the position of a line segment in this figure is needed. So we can arbitrarily draw a line AB here, So at time t equals 0. Then we have this AB. Maybe it have intersect angle with the positive direction of x. So this line will parallel to positive direction of x. So maybe we show that this intersect angle will be phi. And this is AB. And we also have the coordinates of A is XA and YA. Then we can use this equation. So the position of a line segment AB can be determined by the coordinates of point A. Let's say XA will equal F1t. It is a function of time t. And YA will be another function of time t. And phi, phi will equal maybe the phi 0 plus another f third t, right? So the position of a line segment AB is arbitrarily selected from this plane figure, So we just need to determine the coordinates of point A and the angle between AB and the positive direction of axis X. Therefore, the position of figure S can be determined by these three independent variables. These three things is independent. So can you guys remember that we have talked about that? A free body in the plane. So you guys can think about we have a free body on a plane. Let's say we have a free body like this. So in the first part, statics of our course, engineering mechanics 1, we talk about if this body, the free body on a plane, right? We call that it will have three freedom. Or we can see, in other words, we can say it have three kind of capable of movement. Do you guys still remember? I have said that. It's three independent capable of movement is a movement along x-axis. Maybe it can move along y-axis. It also can have some rotation around some axis. So that is three freedom. So actually we can just use this, and this to denote these three kind of movement and these three kind of freedom. That's why actually this is the equations of a plane motion. If we see at different time when let's say this is when time t equals 0. Maybe at other time t equal t, and this body move to here and also have some rotation. Maybe our AB will be like this. So this A prime and B prime. So we will find a coordinate system will be different from the initial position. Its orientation that the angle between AB and X also changed from phi into this phi prime. So that means we will have three equations to denote the plane motion. So can you guys understand my description here in this page? I think it's not difficult to understand, right? It's not difficult to understand. Then we can move on. So our equation of a plane motion can be written at this. So xa will equal function 1t. So it is time of time t. And ya is another function f second t. And angle, rotation angle will be f3t. So actually we can divide this into two parts, you know? So this part means translation. Right? And this part actually is the rotation equation, rotation. See? So actually, if we use our right-hand rule to denote the rotation direction, it may be CW direction or CCW direction, right? So actually, its vector will perpendicular to our plane, our reference plane. And this translation will always on this plane. So that's why this rotation is independent to this translation. Actually, movement along x direction and movement along y direction also independent to each other. So this guy and this guy also independent. So that's why we said that this three motion is independent from one to each other, right? So the xa, ya, phi can be found from this equation at any instant time t, and thus the location of plane figure S can be determined. So that's the equations of a plane motion. I hope you guys can understand that, right? I hope you guys can understand that. So let's continue to talk about the plane motion, its decomposition. So because these three ones are independent, so we can assert that. So plane motion can be decomposed into translation and rotation, just like this line. We divided these three equations into two parts. So the first one and the second one denotes the translational part, and the third one denotes the rotational part, right? So when point A in the figure S keeps static, see, please you guys follow me. Think about that. When point A in the figure S keeps static, that means XA and YA will never change its position. Then the rigid body rotates about a fixed axis. It's not a plane motion anymore. And when the angle phi in the figure S keeps unchanged, then the rigid body has translational motion. So you guys can find, actually we can set that our translational motion, our rotation, actually we can think about that. It is a special, at PECL, special kind of plane motion. So do you guys agree my point here?
Yes, yes, Lars.
Does anybody still listen to me?
Yeah, لو
I
yes.
can hear
Yes, that's
no
it.
any reply from you guys. So from the description here, maybe I think you guys have talked to me, but maybe there are problem from my. Let's see. So anyone who can say something.
Hello, I
Okay, it's my problem. Maybe you reply to me all the time, but I
yes.
I should change this configuration. So I don't know, actually I have two I have two devices. So this device is voice very low, so I cannot hear your voice. Okay, okay, I'm very glad that you guys always reply to me. I will continue our introduction. I think this part is not that difficult, right? I think you guys can understand that, right? So we have finished here. So from these two sentence description, we can think about our so-called simple motion of raised body. All can be considered as a special kind of plane motion, right? And therefore, a plane motion can be viewed as the composition of a translation and rotation, because these two parts cannot cannot affect to each other. That means rotation cannot affect translation. Translation also cannot affect rotation. This two part is totally independent. So although actually, if we say a rigid body have a have a plane motion, that means it have translational part and also have rotation part at the same time. We can think actually this time can be look at two terms. So although actually these two parts happened at the same time span t, but we can think actually this rigid body first have translation movement at the first time t, then its translational will finish, and then it only have rotation. And this sequence can be changed arbitrarily because these two parts are independent. So this principle we call that 运动叠加原理. That's how we can divide complex movement into two simple one to another analysis. Then it can totally simplify our analysis difficulty. 运动叠加原理。叠加原理 in Chinese may be superposition, principle of superposition. That means although these two parts happens at the same time, but we guess, we think it happened from one to each other, right? In the sequence. That because when we look at this, the one components of motion is very easy to study, right? Because that motion superposition may be the principle of motion superposition. So let's continue. Consider you are a gentleman, you're sitting on a car, right? Your car have a beautiful window here. So here maybe you are, I'm not good at drawing, but maybe you are a face. You just look out from through the car's window. So if you look at the wheel of your car, and let me give you a reference point. If you just see this point B from the car, let's say this car have a uniform velocity along the positive direction of x, then you can find actually this point B will have a circular trajectory. See, you will find actually this point P is rotation around the fixed point A, right? So because you are sitting on the MCS, see? You're sitting on MCS just from the principle we have learned from the last chapter, chapter 8, right? So number 18, thank you. You totally understand what I'm trying to talk about, right? But if we are sitting or standing on the ground, we look at the same point. Then, because this time, it will have rotation around point A. It also have horizontal movement, right? Then we will find actually this time if we stand on the fixed ground, then this point B will have a very complex trajectory. We call that in Chinese 摆线, right? So that means the same point, its movement is absolute, but when we try to describe its movement, we will have to select a reference object. Then, because we are using different reference object, then we will give totally different description of the movement of the point, right? So that's why if you're sitting on the car, you will say its motion is very easy, just a rotation. If you're standing on the fixed ground, you will see its motion is very complex. It is a plane motion, right? So let's see. I will erase all I have right on the screen. So you just see the plane motion of the wheel. Actually, you can totally ignore the yellow part. You just consider we have a wheel, right? It rotates on the ground. So if here means t equals 0, then the other time moment, maybe this wheel will run to here, right? Its position of A is different, and it also have some rotation angle, right? So that means the plane motion of the wheel can be viewed as composition of translation with the vehicle. That is what we said, VE, right? And the rotation relative to the vehicle, that's what we have in the VR, right? So plane motion of the wheel, that means if we look at this wheel, it's a rigid body. So it will have plane motion. The plane motion of the wheel relative to the static reference. Okay? Relative to the static reference system, our SCS, means its absolute motion. Translation of the vehicle body moving system relative to static, we call that transport motion. So because if you are sitting on the car, because the movement of the car, you will have to movement with the car. That means transport. More like this car will drive you from one position to another position. This is called transport, right? So that's what we have learned from the chapter 8. And we also have rotation of the wheel relative to what? To the vehicle. So, you know, this is the VE. This is the this is the VA, this is VE, and this is VR, right? So it implicates, it told us that we can use this principle about VA equal VE plus VR to study the complicated plane motion. You know, so actually, if you guess totally understand what we have learned from chapter 8. So you will find actually chapter 9 is very easy to study, right? So let's move on. The arbitrarily selected point A is called a pole. A pole maybe, I think it also have mean hole. So in Chinese, we call that 基点. I think 基点 in Chinese, in English translation, should be basic point. Basic point. So I am the first time when I talked to the mechanical engineering 2020, I think this is very confusing to me. But later I think this is quite very correct description of this. So you guys can think about that. So if we have a plane, so please follow my description. We have a fixed plane X, O, and Y. We have a plane figure which have plane motion. So we can think about that. We use a pole that's a long road, a long road. Let's from this vertical direction, which is perpendicular to this plane, this plane, this rod will poke a hole into here. So can you guys understand my description? We use a long rod to poke this plane figure into a hole. So and we should get let this long rod stay in the hole. So and then we fixed a MCS X prime and Y prime on this rod, O prime. This kind of MCS. So you guys can think about that. Please pay attention to my description. So because we know this is a plane motion figure, right? It have a plane motion. So it have two motion part. One is translation. So when this plane figure had the translation part, then our rod and our MCS, which is fixed on the rod, will have to follow with this translation because when this plane is translation part will let this pose position change from one position to another position. That means this pole, this rod and this MCS have to move with this plane. See? But when the second part, rotation part, when it's rotation, when the plane rotation, then you can find actually our rod and our X prime, Y prime do not need to move with this rotation because when this plane rotation, because there is a hole, so you can rotation yourself. Our rod and our X prime, Y prime do not need to rotate, right? So it's more like its rotation will around this pole. So that I think the reason why English use this 基点 in Chinese with the pole. So it's very easy for us to understand the plane motion in two parts. One part translation means this will have to move with this translation part. But when the second rotation part, it do not need to rotate with it because it can totally rotation without any obstacle. That means our rod will not put some obstacle to its rotation part, right? So let's see. Let's say we also use this wheel to talk about description of plane motion. Plane motion of a wheel. You guys look at this picture. So a plane motion of a rigid body can be decomposed into a translation with the pole. So think about what I have told you guys from here, and the rotation about a pole. You know? So a translation with the pole and the rotation about the pole. And this position of pole you can arbitrarily select on the rigid body. So that means you can pull this plane figure here, maybe at point A. You can poke it at this point B. It will have no different into these two decomposed, right? Maybe the translational description will be different, but the rotation will be totally unaffected by this different position you select. So that means you can think about that. If we select this C as the basic point of the pole, so let us draw a reference section AC here. So if this wheel from t equals 0 to t equal t prime, maybe this wheel rotate from here to here, from the yellow position to the shallow blue position, right? So we can think about that. This plane motion can be decomposed into translation. You can think about that. First, we will just have translation movement. This AC will just along this trajectory with translation part from this position to this position, you know? So this A prime and C double prime. Then that means it translation part is finished. Then at this position, we will have this C prime, A prime will rotate an angle around this point A prime. Then C double prime will rotate to its final position C prime. See? Actually, this translation and this rotation, it happened simultaneously, but we can decompose into two parts. So we can think about that translation happened first, then rotation happened second. T1, T2. We also can think about that. So first, it can keep the original position, but let its CA rotate with this angle, this phi from C to C double prime here. Then it translation with this orientation never change from here to here. See, we'll always the final position of this wheel. So that's why we can decompose a plane motion into two parts. No, so that tells us why a plane motion of a rigid body can be decomposed into a translation with the pole and the rotation about the pole, right? So you guess? Translation with A, let's say use the time t. Then let's say this is C1 double prime, right? Then rotation about the pole A with the delta phi, with another t. So actually this translation and this rotation happened simultaneously, 是同时发生的。You know, happened simultaneously, 同时发生的。I think should be simultaneously. simultaneously. Maybe I cannot write correctly, but you guys should know this meaning, right? But in order to simplify its motion, we can think about actually it is translation first, then rotation second. Can you guys understand this description? Can you guys understand that?
Yes.
Okay. If you guys can totally understand, then next time we'll talk about how to use this theorem. So if we select a point on this rigid body, let B, let's know its velocity VB, and any other point on the same rigid body, let's say M. So we try to figure out its velocity, so we can use this kind of thing. We can first link about this M. So because this VM will have two parts, one part is translation with VB, so it will have VB part. The second is it will have a rotation around the point B. So let's say it will perpendicular to this link MB. So let's say this is VMB velocity. So then we can give a parallelogram. So we link its diagonal line here, and this will be its absolute velocity Vm. That we are going to learn next time we have this measure. Vm means any other point on the same rigid body who has a plane motion. It will equal its translation with the pole point and its rotation around the pole point. And you know, actually this VMB will equal omega MB. Actually, it's rotation angular velocity of this rigid body and the distance from M to B, LMB. And the other things is the translational moment or translation velocity of pole point. So this is a very important theorem, just like what we have learned, VA equal VE plus VR. So next time we will learn that further. We will do some examples. I think that's all for today. 我们今天就学到这里了，下课吧，好不好？再见，同学们，拜拜，you guys. That's all
Thank
for
you,
today.
老师。拜拜。
好的，再见，再见。
再见。
See you next time.
老师，再见。
再见，谢谢大家。
See you later.
拜拜。
拜拜。